Hello students, welcome to this class. This is a demonstration class on refraction of light through rectangular glass block. Before we go into this demonstration, we would like to first look at some terms. What is refraction? Refraction of light is the bending of light, the bending of a ray of light as it travels from one medium to another of different densities. The bending of the ray of light is made possible because of the difference in densities of these two mediums. The density of the mediums affects the speed of the light as it travels, so that as the ray travels from one medium to another medium, because the density of the mediums are different, it reduces the speed of the light. That is, if it is traveling from a denser to a less dense, or increases the speed of the light if it is traveling from a less dense to a denser. This change in speed causes a change in direction, and this change in direction is what we see as the bending of the ray of light, and that is what we call refraction. In this demonstration, we are considering a ray of light traveling from air into a rectangular glass block, and then it comes out through the other end of the glass block. So if we compare air and glass, we know that glass is denser than air. So the ray of light travels from air, a less dense medium, through the glass, a denser medium, and then comes out into air again, a less dense medium. So traveling from air, a denser medium, into glass, because the glass is denser than air, the speed of the ray of light reduces. And then when it comes out on the other end, the speed increases. And so this change in speed causes the ray of light to bend. And then when it comes out, it will bend again, which is what we call refraction. It is important to note that if the ray is traveling from a less dense to a denser medium, the ray will bend towards what we call the normal. The normal is a vertical line that is drawn perpendicular to the boundary between the two mediums. A vertical line that is drawn perpendicular to the boundary between the two mediums is what we call the normal. So for a ray of light traveling from a less dense medium into a denser medium, it will bend towards the normal. And then when it comes out from the glass block, which is the denser medium, into air on the other face, because it is now traveling from a denser to a less dense medium, it will bend away from the normal. So that's refraction. So in this demonstration, like I mentioned before, we will need a rectangular glass block, and then we will use 4 optical pins, 2 as object pins, and the other 2 as image pins, which we also call the search pins. And then I have 4 thumb pins. The thumb pins will be used to hold the drawing papers. A drawing paper where the ray diagram will be drawn, showing the refraction. And then finally, we need a drawing board. Then other apparatus or other instruments from your mathematical set that you also need: a protractor. The protractor is what you will use to measure your angle, the angle of incidence, the angle of refraction. You need a ruler 30 cm ruler for drawing straight line, and finally a pencil for your ray diagram. So the first step is to attach the drawing paper to the drawing board using the 4 thumb pins. Using the 4 thumb pins, you attach the drawing paper to the drawing board. Next, you place the rectangular glass block on the drawing paper to draw an outline of the block. And so you remove the glass block, you have the outline on the paper. You label the rectangle A, B, C, D. Rectangle A, B, C, D. The outline of the rectangular glass block. Next, you use the protractor to draw a normal at the face AB of the outline. You place the protractor at the face AB and draw a normal there. I use my ruler to draw the normal, which should be a straight line, a vertical line. That's the normal. We can measure a given angle of incidence. An angle of incidence that we will work with, 30 degrees. So the angle of incidence is the angle between the incident ray and the normal. So between the incident ray and the normal, we measure an angle of 30 degrees. So we have 30 degrees here, from 90 to 80, 10 degrees, to 70, 10 degrees, and to 60, another 10 degrees. That gives us 30 degrees. So with this ruler, we join the points to get a straight line. This is our incident ray. To show that it is a ray, you put an arrowhead. A straight line without an arrowhead is meaningless as far as optics is concerned. So for the ray, the line to be recognized as a ray, there must be an arrowhead showing the direction of the ray. Very important to take note. So you put your angle 30 degrees. At this juncture, we will replace our rectangular glass block on the outline. Then we fix the 2 pins, which we mentioned at the beginning that they are the object pins. 2 pins. The 2 pins must be reasonably spaced and vertically erect. These are 2 precautions that you take when carrying out this experiment. The pins must be reasonably spaced and the pins must be vertically erect. They must not be tilted. Then, using the other 2 pins, which we call the image pins or search pins, you will look for the point where there is no parallels between these 2 object pins on this other face of the rectangular glass block, the face labeled DC. You look for the point where there is no parallels. The point where there is no parallels is the point where these 2 pins will be on a straight line. The 2 object pins will be on a straight line, along with this search pin that you are going to fix on this other face, DC, such that when you are viewing this pin, the search pin on this face, DC, you will not see the other 2 image object pins on the other side. That is the point where there is no parallels. So to obtain that point, you will view the pins on the face DC of the rectangular glass block. Once you have located that point, you put the search pin there. Then you use the other one following the same procedure. The point where you will see only this second search pin and the first search pin as well as the two object pins will be blocked by the first search pin. That means you'll be seeing only this search pin in front. You cannot see the second search pin and you will not see the object pins. Once you locate that point where there's no parallels, you fix the pin there. Once you have done that, the next thing is to mark the points where the pins are located, because you will draw a straight line to join these two pinpoints to the face DC of the rectangular glass block. So you remove the glass block, you remove the search pins, as well as your object pins. With your ruler, you draw a straight line joining the two pinholes to meet the face DC of the rectangular glass block. Then, the point where the line touches the face DC of the rectangular glass block, you will draw a straight line to meet the point where the incident ray touches the face AB of the rectangular glass block. You join these 2 points with a straight line. As usual, you put your arrowhead on the line, that's a ray, and the arrowhead on the other line, which is also a ray. This line inside the rectangular glass block is what we call the refracted ray, while the line that is outside the rectangular glass block on the face DC is what we call the emergent ray. If you draw this incident ray as a straight line that continues with a broken line, it is expected that the incident ray produced with a broken line should be parallel to your emergent ray. If it is parallel, then it means your emergent ray is accurately drawn. If it is not parallel, then it means there is a mistake there and you repeat. The perpendicular line between the incident ray produced and the emergent ray, this perpendicular line is what we call the lateral displacement between the incident ray and the emergent, the lateral displacement, and it's usually labeled as X. Then finally, we can measure our angle of refraction using our protractor. The angle of refraction in this case, the angle between the normal and the refracted ray. The incident ray is labeled I, the refracted ray is labeled arrow, small letter arrow. Incident ray, incident angle, small letter I, refracted angle, small letter arrow. So if we measure the incident, the refracted ray, that will give us so beginning from 0, the angle we have here is 16 degrees. So when I, angle of incidence is 30 degrees, small letter arrow, angle of refraction is 16 degrees. And so we can also do more demonstration for angle 35 degrees, angle 40 degrees, angle 50 degrees, and so on. I will have different angle of refraction. And then the sine of the angle of incidence, when plotted against the sine of the angle of refraction. When we say sine here, we mean S-I-N-E, sine, not S-I-G-N, but S-I-N-E, the sine of the angle of incidence plotted against the sine of the angle of refraction. A straight line graph is obtained from such a graph. And the slope of this straight line gives us a constant, which we call the refractive index of the rectangular glass block. The refractive index of the rectangular glass block. So this is what we popularly refer to as Snell's law of refraction. Snell's law of refraction, which states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant called the refractive index of the second medium with respect to the first. And so here the second medium is glass, where air is first medium. So the refractive index of glass will be the ratio of the sine of the angle of incidence to the sine of the angle of refraction. So that is how Snell's law of refraction is verified, having a straight line graph when these parameters are plotted. So that is our demonstration for this class. I do hope you have learned a lot in this class. So if you have any question, send in using your notes and question plugin in the portal. Waiting to hear from you. Bye for now until our next demonstration class.